Welcome back. We have audio and we're sharing our screen. We had a request for roadmap winter 19 and then this one, I think we'll do this one first. It's shorter and then the roadmap was for some selections, which I'm not too sure which ones we want to do. This one illustrates what I had on page 1, or I don't think it was 1. It was here. Remember I crossed this box off because I forgot to put a methyl group on here? Well, in the one we're about to do, the methyl group is there. So I wrote a new comment, see winter 19, page 8 today. Here's page 8 today. And here we go. It's got a methyl group. So your two choices of alpha H's after you identify that the acid is here. Now, normally we think of alcohols as pKa 17 to 18. I don't emphasize this too much, and you would get full credit for saying 17 right here, but I cannot, as an organic chemistry instructor, pretend that ethanol or methanol have a pKa of 17 when they have a pKa of 16. Those two alcohols are identical, they're almost identical pKa's to water. Once again, you would get full credit for 17 there. Do not fuss. And then the H's in question are the alpha H's here or here. The alpha H on the carbon with the methyl is superior because the resonance form of this anion has a more substituted double bond between the former carbonyl carbon and the alpha position. And a reminder, why is this resonance form much better? The main reason is it's got a minus on an O instead of a minus on a C. And the other alpha position, minus on carbon, and resonates to a double bond between the alpha position and the former carbonyl position. But the double bond is less substituted here than it is up here. So we filled in our missing pieces. Now we did the more stable resonance forms for the pieces as well. Now pKa's, we didn't do the alpha H. That's one of our new ones. Alpha H is 20. pKeq equals 20 minus 16. KEQ equals 10 to the negative 4. And we are definitely circling the arrow towards the more stable acid, which is the one to the left. 20 is more stable than 16, and I believe we did everything we need to do. And then I'm going to need some help because we can't do a roadmap in 24 minutes. So I need the questions that were giving you a little trouble from Winter 19, Part 2.
Professor?
Yeah.
It's the left bottom.
It's the bottom?
Yep, like when we have like these 3 arrows going down.
1, 2, 3? Okay, I like it. Very specific. We'll zoom in down there. We'll get over to the MMPP. I think we zoomed a little too far, believe it or not. There we go. So MMPP will react with an alkene to make an epoxide because MMPP is magnesium monoperoxyphthalate. It's a peracid, just to remember that. It's for making epoxides. Let's see, every product has a cyclopropane with at least one more carbon all the way to the end. That's a good circle for R. Cyclopropane with one more carbon. R equals. So we've got R going to, used to be an alkene, and now it's an epoxide. Similarly, It doesn't have to be a wedge there. It doesn't. Let's do a nicer drawing. There. Similarly, bromination in water creates a vicinal halohydrin. If you want a quick review on that, step 1 gives you this intermediate with a more electronegative O on the more substituted carbon, less electronegative Br on the less substituted carbon. A base will take the H off the O to make an O minus, which will make an epoxide. Kick off the Br. So we're going to have goes to CH2, goes to a C with a cyclopropane. And the epoxide's on the left of the methyl here. And there you have it. And now it's all about opening epoxides, isn't it? So what's going to happen? We're going to open up our epoxide here. So we need to create, there's R, just in case you're having trouble seeing it, there's R again. And it got opened up on the less hindered carbon. This is the more hindered here, less hindered with C-triple-C. So step 1, open it up with acetylide, HC-triple-C minus. I don't need to see a counter ion as long as I see the anion. And that will generate an O minus over here. And there's an O minus on the carbon with an ethyl. So that's this one here, carbon with the ethyl. And then I need the O minus to make a new bond here. That's a new bond right there. I'll highlight it. You made an O minus when you reacted part 1. And it looks like it made a bond to a carbon here with an alcohol on the adjacent carbon. That too is an epoxide reaction when you have a nucleophile attack one carbon and an alcohol shows up on an adjacent carbon. The other option I believe will happen shortly, and the alcohol ends up on the same carbon that got attacked. I don't know. We'll see. 2. We need an epoxide with how many carbons? 1, 2, 3, 4, least hindered, more hindered. And there we have the epoxide right here. It'll be an O, and it has an ethyl after that. And that will generate an O minus here. There'll be an O minus after the epoxide's opened by the O minus from here, which was made during step 1. And that needs to be protonated. Clearly, it's an OH when we're done. And you have that result. Now, from this epoxide, it looks like this one's even simpler. Here's the new bond right here. Our previous one, we had 2 new bonds. So you want highlights on the new bonds. That was opening up the first epoxide, generated a nucleophile to open up the second epoxide. This one's more straightforward. Just need an O minus nucleophile to attack the more hindered or less hindered carbon. Less hindered carbon. And we'll talk about getting it on the more hindered carbon shortly. So remember, strong nucleophiles attack more less hindered carbons. I keep misspeaking. I'm sorry. Strong nucleophiles like acetylide or isopropoxide attack the least hindered carbon. In this example, it's here. In the previous example, it was there. And that would generate an O minus up here. This would break right here after the nucleophile attacked here. You want the mechanism to get the attack going? Why not? Doesn't hurt. The attack on the least hindered carbon generates an O minus. And you get an O minus to be an OH the usual way. Step 2. HCl. There's a reason why this is 2 points, because 2 things happened, and this one thing happened. And a protonation doesn't get you a new point. Okay, now how do you get the O to attack the more hindered carbon? Well, this is the one where cations are involved. How do you generate a cation? You protonate the O first with a strong acid such as sulfuric acid. That will protonate the epoxide. Now, if you do it in the solvent isopropanol, then that's your nucleophile. It's weak, but you have an activated epoxide. So weak nucleophile is okay. So if you request it, we can do this mechanism as a good review mechanism. Otherwise, we'll just leave it as is. Do you want to do that? Or do you want to do another part of this roadmap? It's up to you.
I have another part.
Sure.
It's
Is
in the
is it
other
showing?
side.
Over here or further
Yeah.
over there?
Yes. Yeah.
And
This one, the last one.
the last to going to here? From here?
No, like from the last one going up.
This one. Okay, so we know this molecule and we have to make this one is what you want to do now?
Yes.
Okay,
Please.
let's do it. It's a great question. All right. So what we have here is a protected alcohol with DHP. And so somewhere along the way, we have to deprotect it, right? Because there it is without its protecting group. We know that.
H2SO4.
Yeah. And here we have an aldehyde from a terminal alkyne. That's useful. Aldehyde with a second carbon there from these 2 carbons here. And that is an old review reaction. Why is it a very relevant review reaction? What is the title of chapter 16? Aldehydes and ketones. Every reaction that we learned previously to make aldehydes and ketones is fair game for this test. That's why the chapter starts with those review items. And so we're going to do the conversion to the aldehyde first from a terminal alkyne. This is a terminal alkyne. We're going to use the chemicals. If you use BH3, I'll give you partial credit. It doesn't give great results, but it would give some aldehyde. The boron with sec isoamyl borane is this one. Sec isoamyl twice. That's that. And that would be followed by always hydroborations followed by hydrogen peroxide and hydroxide. So that gets us to the aldehyde portion. And now you just have to deprotect your protected alcohol. And that would be sulfuric acid and water. You just need to say H2SO4 AQ. And once again, side product is the hemiacetal over here. And I bet there's something else you want to do.
Yeah, can we do like all the way up, like to get it to hemiacetals?
All the way up?
Yeah, just to get the hemiacetals and the acetal.
The
That's
hemiacetal, acetals, where are those at?
it's the same side.
Oh, it says hemiacetal. Okay. Oh, yeah. I see ya. So we're gonna go make a hemi here. Do we have all the pieces we need to make hemi and then acetal? We do. We have a carbonyl in our aldehyde, don't we? And we have 2 alcohols. 1 alcohol will make the hemi, and there will be 2 of them. So since we're not restricted to boxes on our test, why don't we just make this a double box? two products, two hemiacetals. I could have this O attack the carbonyl. And reminder, CHO looks like this. All right. So how big will the ring be? We're going to go from this O all the way to the carbonyl. Don't use that highlighter. We already used it. And we're going to go from the O to the carbonyl carbon. And that will be ring size 1, 2, 3, 4, 5, 6. And the aldehyde will become an alcohol. The hemiacetal has both an ether and an alcohol. So we'll do it in light blue. Go with our light blue highlighter. And we're going to have ring size 6 with O going to a carbon that's got an OH. And the O ring size 6. And having trouble keeping score here. We'll count the O as 1. And then the C is 2, 3, 4, 5, 6. And this is 6, 5, 4, 3, 2, 1. What's on 2? Two things on 2. We have an ethyl and we have CH2R. Remember, we did an R a long time ago. It was the cyclopropyl CH2. What's on 3? A methyl. And feel free to do this on tests in the future. 4 has CH2, CH2, then R. And I think we have all the parts. Now the other hemiacetal will be in purple. Going from this O, it's not going to be a very nice hemiacetal. 1, 2, 3, 4. The other O attacking, I think you'd get very small amounts of this. 1, 2, 3, ring size 4. Yuck. O goes to C with OH. And we're going to need other number. Do we need other numbers? Probably. The O was called 1. The carbon that got attacked was 4. 3, 2. What's on 2? 2 is CH2, CH2R. CH2 once, CH2 twice, R. And then 3 has a methyl. 4 has, did I do that right? Where's 4? 4 has just the thing there. Seems like I'm missing a lot of stuff. 4 also has this whole big chunk up here. I used 3 does not have a methyl. Purple 3 does not have a methyl, Dr. Whitaker. Somebody's going to say that. Don't have to say it now. Purple 3 has nothing. It's a CH2. Purple 2 had that group there, and then 3, 4. Purple 2 also had this monster up here. So purple 2 goes to a C that has, hello, that's an eraser. Pen. Purple 2 has a C with a methyl. The C with a methyl goes to a C with an OH. With an ethyl. CH2 once, then R. And that's the other product. We probably get 0% yield, but you were asked for 2. You've got to do the other one. Okay. And then they're both going to form an acetal. That's the fun part. They're both forming an acetal. Did I miss something over here? Carbon 2. Carbon 4 in pink also had an OH. I don't have carbon 4 with an OH, I see. Carbon 1, 2, 3, 4, 5, 6, 4. I didn't draw this OH. And the reason I got confused now and not earlier is I need that OH now. Now remember, what happens during acetal formation is that the other alcohol attacks where the old alcohol used to be. This one's going to be eliminated by protonation and then resonate and make a double bond. The double bond is an activated carbonyl gets attacked. Basically, what I'm going to do is copy everything here up here, except for the OH and except for the H. There's your water. Lose the OH, lose the H. I'm going to connect this O to the former carbonyl, which is 6. I'm going to do my best to copy everything in blue except for the OH. Okay, my pen is stopped because it's off. All right. So why not? Already outside the box. Okay. And you want to do the alcohol on 4 is now just an O. I'm going to stick it up here. And there's the 5. Wait, did I do that? No, it's one more carbon over. Do the numbers. Is this 6? 1, 2, 3, 4, 5. That's what's my problem. It's not a 6. Ring size 6. I'm not going to put the pink numbers on so I don't mess up again. The 1 was the O, the 6, 5, 4. 4 is the other O. 4 had an O, which is now attached to, you guessed it, 6. And the number 6 is in the way. This is more fun than we should be having, isn't it? And hang in there, everybody. We're almost there. There's that. And there's a new bond there. And make sure you have off 4, a CH2, CH2R. CH2, CH2R, just like we had before. Off of 3 is a methyl. Off of 2 is an ethyl. And a CH2R. You would have had the same result with a slightly different look if you connected this O to the carbon that's right here. And this would go away, and the H would go away. It would just be this drawn with a slightly different angle look. Same molecule, though. It's a little easier to see it from here. Don't think I missed anything there. And that's an acetal. How do I know? It's ether there and ether up here. And that is that. And any last minute questions?
I do have a question about the lecture. I have a question about lab.
Lab question. Can you, I'm going to check my email as soon as I start, hit the stop button on this, and I will look at my email for your question, I promise. And yes,
Sure.
lab this week is virtual for all my students in lab.
So does that mean it's for experiment 4 or?
No, it's going to be something you haven't seen yet, and you will see it tomorrow. If that was your
Sure.
question, then we're good.
Yeah.
I will still check my email though. All right, everybody. So I'll see you Wednesday at, try to be there 6:20 just to be safe, okay? You know, I like to do things a little early, but 6:20, and you want to be settled in as soon as you can to get your full 2 hours in. Okay? All right. We'll see you then.